Have you ever wondered how the astronauts managed to get to the moon? In 1961, President John F. Kennedy set out a mandate for the United States. This nation should commit itself to landing a man on the moon and returning safely back to Earth. At that time, there were more questions than answers. What energy supply could be used to propel a spaceship such vast distances while safely powering the onboard electronics once in orbit? What could keep the astronauts warm as their ship traveled through the sub-zero temperatures of space? How could the astronauts carry enough drinking water on board for such a long voyage? NASA engineers wrestled with these problems and others. Nuclear power was too dangerous to use, batteries were far too heavy, and solar panels were not yet a robust enough technology. These answers was found in a technology that was first invented in 1839 by Sir William Grove, and first successfully produced in 1932 by Francis Bacon, the hydrogen fuel cell. Hydrogen fuel cells became the obvious choice for space missions. They run on a clean fuel to produce the electricity for the ship's energy needs with two important byproducts, heat and water. The heat and water produced by the fuel cell kept the astronauts warm and hydrated as they traveled to the moon and back. It could even be used as rocket fuel to get the space shuttle into space. It was in the beginning of the 1960s that engine aircraft manufacturer Pratt & Whitney licensed Bacon's patents for the alkaline fuel cell. NASA then decided to use the AFC fuel cell to power their spacecraft. These fuel cells, however, require very pure hydrogen and expensive platinum catalysts to ensure clean operation and long life. Because the fuel was so pure, the fuel cell's waste was clean enough for the astronauts to drink. The alkaline fuel cell was for a long time considered a mere scientific curiosity. Francis Thomas Bacon was a forerunner in fuel cell technology. Bacon was fascinated by the ability of fuel cells to directly convert chemical into electrical energy, and he became convinced of their usefulness. During the 1950s, the Bacon cell emerged as the leading fuel cell technology, with a 6-kilowatt version demonstrated in 1959. Pratt & Whitney subsequently licensed the design to power the Apollo space vehicle, an improved version of which supplied electricity for the space shuttle. The Bacon cell failed to find a niche outside of space application, owing to its requirement for pure hydrogen and oxygen. Its success in that role served as a technical beacon of the period and inspired research on many other fuel cell operating systems. During the 1970s and 80s, the cost of catalysts and limited materials availability restricted the alkaline technology development. Moreover, while the companies recognized that alkaline fuel cells' intolerance of carbon dioxide, one of the major disadvantages of alkaline fuel cells, and the difficulties and high costs of overcoming the problem were an insurmountable barrier for commercialization in terrestrial applications. Other chemistries appeared to offer alternative routes to power at a more acceptable cost. However, it also became apparent that specific chemistries suited certain applications. There was no single best technology. With 23% less CO2 emissions than a diesel generator, ammonia-fed alkaline fuel cells are beginning to replace diesel generators. Alkaline fuel cells has proven to have 14% higher electricity generation than a diesel generator. The worldwide production of ammonia amounts to 100 million tons per year and is one of the most used chemicals produced from natural gas. The use of small amounts of ammonia as a gasoline additive is proposed to make a combustion engine exhaust gas absolutely nitrogen-free. Alkaline fuel cells are not very sensitive to ammonia in the fuel, since the electrolyte rejects ammonia, and the residual ammonia and the hydrogen can be recirculated through the dissociator catalytic heating unit. The whole system, ammonia dissociator plus alkaline fuel cell, is characterized by a simple design and high efficiency.
Here you can see the diagram of an ammonia-fueled alkaline fuel cell. From the ammonia tank, it is sent through 3 preheating chambers before it reaches the cracker, where it is then heated up to 300 degrees Celsius, thus separating the nitrogen gas from the hydrogen gas. The hydrogen is then sent back through the 3rd preheating chamber before it reaches the cathode of the fuel cell. From there, it's sent through the 2nd preheating chamber before it reaches the heater. Here it is combusted to heat up the cracker and then vented off into the atmosphere. The electrolyte of the fuel cell is a mobile electrolyte which flows through a heat exchanger cooled by air before it reaches the electrolyte storage tank. It is then pumped back through the fuel cell as it is a mobile potassium hydroxide electrolyte. On the anode side, air is brought in through a blower and scrubbed through a carbon dioxide scrubber in order to remove any harmful carbon dioxide, before it reaches again the anode of the fuel cell stack. From here, it is vented off through the first preheating chamber before it reaches the atmosphere. Current is then drawn from the fuel cell in addition to any external energy storage in order to power whatever load the fuel cell is hooked up to.
Alkaline fuel cells can currently be used as the primary power source of boats and golf carts. The alkaline fuel cell powered boat is quieter and much more efficient than the typical gasoline-powered engine. The AFC boat does not release carbon dioxide. The only byproduct is water vapor. Since the fuel cell only rejects water, this makes it favorable when comparing it to a gasoline engine. Mike Stritsky collaborated with Duffy Boats and other partners to develop the first zero-emission, hydrogen-fueled public water taxi. The boat is powered by a fuel cell engine from Anuview Incorporated and was demonstrated for attendees at the World Maritime Technology Exposition. The partially government-funded boat illustrates the real-life feasibility of environmentally conscious marine transportation initiatives and the specialized features that Anuvu's fuel cells provide for the maritime transportation industry. The water taxi runs on an Anuvu PowerX fuel cell battery electric hybrid engine. The result of nearly 10 years of research and development, Anuvu's PowerX fuel cells are cleaner and quieter than current marine vehicle engines. Emitting only heat and water vapor, Anuvu's fuel cells allow government ferries, commercial marine fleets, and recreational boats to have an environmentally friendly engine. Mike Stritsky, with Renewable Energy International, developed a hydrogen fuel cell powered golf cart to serve as a neighborhood vehicle for the Mohegan Nation's New Energy, Environment, Economics, and Education Center. This modified GEM vehicle manufactured by Daimler Chrysler runs on compressed hydrogen, creating no emissions.